class. So this is going to be my first online video. Well, my first of many. Where again, bear in mind, we're getting used to the platform. I'm practicing, hopefully making the sound better. Right, working through it. So first is going to be applications of exponential base e functions. Right, now, before we went on break, remember we had derivatives of logarithms, derivatives of exponentials, and if I have time, I might post a video on those. And so in this section, 4.4, we're going to expand the applications. So we already did a little bit with finding tangent lines with exponentials and logs, finding, simple maxes and min, rates of change before we went on break. And so now 4.4 is going to expand that. We're going to look at other types of applications, hopefully reintroduce to you exponential decay, both uninhibited and then the logistic types. Alright, so today we're going to get started into, first couple of problems we're going to look at. Here is the revenue function that we're going to solve and then optimize for. Alright, so we have a function, right, P, which represents the price in dollars of a certain quantity demanded, right, where X represents the number of items demanded. Alright, so we're given the price demand equation. Alright, so price demand up to this point in our applications before has been linear. Now we're going to get a case where it's exponential, right? Price equals 250 at e raised to that exponent. Over the domain 0 to 800, which this is a closed domain, right? My domain starts at 0, stops at 800 with brackets. That means it's closed. All right. Same type of application we've had with polynomials. The new part is the exponential rule. All right, first thing, part A. Find my revenue function. Well, revenue is still price times quantity. The new part is my price equation's no longer linear. My price equation is that exponential price, 250 e raised to that exponent, times another x. Don't forget, times x. Again, that part's not new. The new part is going to be because we now have an exponential in my revenue. Alright, so I'm going to simplify this a little bit because we're going to eventually take a derivative. And so my simplification is just move my x in on the 250. Right? I'm going to rewrite it as 250 times x times my e term. Right? Again, I'm allowed to do that because it's multiplication. Right? I can rearrange it. 3 times 2 is the same as 2 times 3, and that's all I'm doing here. Alright, so there's the revenue function I'm going to use for the rest of the application. Alright, so I've done part A, found the revenue in terms of x. Now part B. Alright, we want to find the number of items we need to sell in order to optimize revenue. So optimizing revenue means I want to maximize it, right? I want to find the biggest possible revenue. Revenue is the generation of sales. And so we want to maximize revenue. All right, remember, it's a closed case, so the setup is not new. It's just when I go to find my derivative, I will have an exponential. Alright, so maximize revenue on the closed interval case, so we'll be using the extreme value theorem. Alright, I have a closed domain 0 to 800. Which means I need to find any critical values on the given domain. Meaning any critical values between 0 and 800. Alright, so again, nothing new. The new part is when will I go find these? I have to find the derivative of my revenue, which is going to require the product rule because I have 250x times the e to the negative 0.025. So multiplication and then chain rule on my e, right? Chain rule because I have something other than x on my e function. Alright, so first thing, write down the first function, 250x times the derivative of the second. So this is where I'm going to take my chain rule on my e. First thing you do, remember, is write down the e function exactly as is. But then I'm not done yet. I now need to multiply by the derivative of the inside part. Well, the derivative of the inside is going to give me the 0.025, just that constant in front of the x. Alright, so first derivative of the second plus the second, which is the e term, times the derivative of the first function. Well, the first function is 250x. 250 is a constant multiplier, it comes along. And so when we take the derivative of 250x, we're going to be left with 250. All right, so times 250. All right, so there's my derivative. All right, new part done. I am going to simplify this because I know I'm going to find the critical value, which means setting it equal to 0. So I'm going to factor. I've got a 250 that I can factor out of each term. I have an e I can factor out. And remember, that will always happen with e because the way the derivative of the e works is you always have the same function there every time. So pull 250 out, pull that e term out to the front. What's left over? All right, we multiply by what's left over. So 250 times e times what's left over. All right, so in the first term, I still have this x, and I have that negative decimal. All right, so those are what we're going to write down. Negative 0.0025 times x plus what's left over in the second term. Well, I factored everything out, right? The e factors out, the 250 factors out. But remember, factoring is dividing it out. So when I divide it out, I'm taking the same expression and dividing it by the same expression. And so I am still left with a 1. And don't forget that 1. It's really easy for students to forget there's a plus 1 there. All right, my next step is to set it equal to 0. So I'm just going to write it over here. All right, setting it equal to 0 because this function exists everywhere. E's exist everywhere. The polynomial exists everywhere. So the only critical value I can get is at a horizontal tangent, a stopping point. All right, so set it equal to 0. And remember, we talked about this before break. The e function is never 0. All right, so the only place I can get a 0 out is this polynomial, this part here. And so when I solve, I'm just going to solve for the 0 in this polynomial. And so that negative 0.025x plus 1 is what we're going to solve. I'm going to kind of ignore e because I can't get a 0 out. And 250, same thing. 250 is 250. Can't get a 0 out of that. And so I'm just going to solve that second part. Alright, so that's the part I'm going to set equal to 0. I forgot my 1. So I'm going to move 1 to the other side by subtracting it. So I get 0.025x equals negative 1. Divide by that decimal. And when you take negative 1 divided by that negative 0.025, you get out a positive 400. And so there's my critical value. All right, I keep it. It's in my domain. It's between 0 and 800. And so the next step is to test using the extreme value theorem, right? This is the closed case. So we input any criticals and endpoints into the original, which remember was the revenue we found in part A. And so I'm going to take my revenue I found in part A, plug in the 400, the critical, plug in the endpoint 0, plug in the endpoint 800. One of those, again, the extreme value theorem guarantees one of them is going to come out of maximum, one of them is going to come out of minimum. I want the maximum, right? I want to optimize sales, I want to optimize revenue. All right, so when you take the 400 and you plug it into the revenue equation, it should come out $36,787.94 and change. When I plug 0 in, it's going to 0, and that should make sense. All right? Revenue is the generation of the money we get from sales. If we don't sell any, we don't make any revenue. All right, and then we plug the other endpoint 800 in, and so when I plug 800 in, we get $27,067.05, and so the first one's the biggest. There's my maximum. This is the minimum, because again, we're guaranteed both, but the optimum value is found at the critical point. All right, so then my answer written, because it's applications. Whenever we have applications, always write your answer with units. All right, so always answer the question, and make sure you always provide units with your question's answer. All right, so we found that if they sell 400 items, they maximize revenue at $36,787.94. All right, so there's the answer to part B. All right, the last part, find the price. So part C, find the price that will optimize revenue. And so we want to find the price. We need to set the item to so that the demand will be 400, because when the demand's 400, we will get our optimum revenue. And so we actually have to go all the way back up here to the price equation that they gave us in the application, and that's where we're going to plug our 400 in, our critical value. So go back to that price equation and plug the 400 into it, and that will give me my optimum selling price. Alright, so when you plug that in, again, I'm going to round to penny because it's dollars. And so when you plug that in, you get $91.97. Alright, and so there's my price. That's my optimum price. If we set our item at a price of $91.97, then the magic happens, right? I'll sell 400 items and we'll maximize revenue at the $36,787. All right, so in this set of notes, we're going to do one more. So I'm going to do problem number 2, which is, again, finding a marginal cost function. So find a marginal cost. So we have a cost of producing X items. All right, so there's my cost equation. So my cost equation is e to the x times the natural log of 2x. So I'm going to have to use a product rule, right? E to the x times the natural log. And then when I'm looking at my natural log, I also have to use a chain rule because there's something other than x inside, and so the chain rule will be involved. All right, remember, marginal analysis is the derivative used in a special way. So when I want to find the marginal cost, I find the derivative. And then the marginal analysis part is how we use the derivative to make a prediction, all right? And we'll talk about that once I find the marginal revenue. All right, so the derivative. This is just basically practice finding the derivative. My first function is e to the x, so I write down e to the x, times the derivative of my second, which is log of 2x. So first thing you do is 1 over the function inside. That's the log rule, 1 over what's inside, so 1 over the 2x function, times the derivative of the inside, so times the derivative of 2x, so times 2, which we will reduce that when I get to the next step. All right, plus, all right, so there's first derivative of the second plus the second, natural log of 2x, times the derivative of the first, which is just e to the x, right? When I have e to the x, the derivative is just simply e to the x. All right, I am going to simplify it because it's just a good rule of thumb to do that. So I'm going to factor out the e to the x and then simplify what's left over. And really, the only thing I can simplify once I pull e to the x out is in this term. All right, the 2's reduce. And they equal 1, right? 2 divided by 2 gives me 1. So I'm just going to be left with 1 over x in the first term. And then plus the natural log of 2x in the second term. All right, there's my marginal cost function simplified. And I didn't ask you to use it, but you should know how to use it. Remember, marginal analysis is a special way we use the derivative to approximate how much one more item, in this case, is going to cost us. And so what we use this for is, again, x is our current level of production. We're producing x items. All right, and so if we pluck x in, the marginal cost estimates how much additional cost the next item will be. All right, remember, it's the additional cost for the x plus 1. So if we were producing 100 items, we'd plug 100 in, but that would tell us about how much more the next one, the 101st, would cost us. So remember that about marginal analysis, and go back and look at some of the previous examples on that. All right, so we're going to stop there today, because we want to keep these videos fairly short. In the next set of lessons, we're going to get into applications where we'll look at where we're given exponential function and look at application types of those. All right, and we'll do a couple of examples where we're given an application with an exponential function and talking about all the different parts and pieces. All right, so we will start there on problem number 3 in this set of notes tomorrow, or not tomorrow, on the next video. So on the next video, we'll pick this up where we'll do applications where we're giving you an exponential function and asking you some questions on that. And that's what the next couple of problems will be. All right, so we're going to wrap this video up there, and we'll start the next one on the applications of E.